Hello, Dr. Chang. Can you hear me?
Yep, I can hear you.
Sounds good. Dr. Chan, I actually have a question.
Sure, what's up?
Um, since you know FEA so much, I was wondering what activity in this class interests you and why?
Which
Um,
activity?
yeah, is there a certain activity that's like this assignment's really I don't know, plays an important role in FEA. This assignment makes use of everything, or from your I want your opinion since you have so much FEA experience.
Sure. I think the one that's really interesting is going to be our optimization activity. I don't remember if that's 6 or 7, but I think that really showcases the power of FEA, because FEA lets you simulate things with basically zero cost. And when you can simulate things with zero cost, you can try out a bunch of different things, a bunch of different designs, without having any kind of consequences, basically. And so optimization it's not really FEA. It actually isn't FEA at all, but it's something that works really, really well with FEA in terms of how the algorithm works and how you can get your results. Because normally optimization is a computer algorithm just in general, but it just works so well with FEA because of just what FEA can do and how quickly you can do it. Yeah.
Sounds good.
All right, so 7 o'clock. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? I hope, right? I will say that I'm very happy to be here. I almost died over the weekend. I went snowboarding in Mammoth with my good friend, one of my very longtime friends. Known him for almost 18 years now. He's getting married next month, and so we threw him a bachelor party in Mammoth. He loves snowboarding, so we went snowboarding in Mammoth. But if you watch any of the news this weekend, there was a ton of snowstorms up in the mountains, and so it happened at a very unfortunate time for us. We were able to get on the lift. We went up to the very top of the mountain, and as we were going up, then the blizzard started happening, and basically the snow was going sideways, and we couldn't see more than 10 feet in front of us. And so, and not great when you're someone like me who doesn't have that much confidence in snowboarding anyway. So, it took me about 4 hours to get down the mountain, but I made it. But there are definitely points where, I thought, this is it. Like, this is it for me. I'm not making it down from this mountain. I'm just going to freeze to death up here. But, very thankful to be alive. God is good. I love my wife. I love my friends. I love my family, all that good stuff. So, I'm glad to be here. I love you guys too. Right. Okay. And so with that said, let's get started with the lecture for today. So it's going to be a continuation of what we talked about last Wednesday. And so if you remember last Wednesday, we were talking about, or all of last week, actually, we were talking more about element types, okay? And so that leads directly into our activity for this week, which is about shell and beam elements. Thank you, Monica. I'm glad I'm okay too. And so today we're going to talk about what shell and beam elements are, how to actually create them in ANSYS, and just what their advantages are. Okay. And so this is a very nice tool, and so it's used a lot, I would say. Not in every project, and so that's why I kind of it's not part of, I wouldn't consider it part of the basics of FEA, but it is very useful, and it's used quite a bit for certain types of geometry. Okay. Okay, and so announcements. Remember, so activity 4 is going to be posted on. I'll probably post it tomorrow, so I'm still kind of catching up on work, from the end of last week. And so I'll post activity 4 tomorrow. We'll do activity 4 on Wednesday, and then activity 4 we do next Friday, just like it normally is. Okay. Remember, the midterm project is out there. I've already gotten some questions about it, so definitely make sure you guys are starting it. You're taking a look, because it is going to take, it's going to be time consuming. Okay, so make sure you're starting that early, because the deadline is going to be on top of you before you know it. All right, any questions I can answer before we get started for today?
Is our homework's gonna be less time consuming since we're supposed to be focusing on the midterm, or do we expect the same length?
They're pretty similar, I would say. So activity 4 in particular, I think is a little bit lengthy compared to the other ones. And so you definitely want to make sure that you're getting work done on the project as much as possible, in between the activities, and in parallel with the activities as well. Yeah. Mm-hmm. Okay, all right, so let's go ahead and get started. And so the topic for today is shell and beam elements. All right, so we started talking about it, probably for the last 20 minutes of class last time, but let's just go ahead and kind of summarize, what we talked about. Okay. And so far, all the element types that we've been using, the tetrahedrons, the hexahedrons, I consider these to be, or what these are defined to be. These are called the solid element types. Okay. And what the solid element types, what they were really designed to do is they were designed to simulate three-dimensional objects. Okay. Okay. Which sounds very obvious, right? And so of course, we're simulating 3D objects, right? And so what's the big deal? And so, why are we introducing new elements, if these already work for 3D objects? Okay. Well, the reality is that, even though, every object that we have here in the real world is 3 dimensions, there are some objects that are more 3-dimensional than others, okay? In particular, we have a lot of geometries that are what I call either very thin or very slender. Okay. So let's say, however, okay. All right. And so a thin geometry would look something like this. And so kind of the most quintessential example of that would be like a thin plate. Okay. Okay. And so you can see from this image here that if we look at 2 of the dimensions, okay, And so we look at basically the length of the plate in this direction, so we'll call that L1. We look at the width of the plate, we'll call that L2. Okay. If we compare that to the thickness of the plate, which is L3, okay, we have L1, which is about the same as L2, which is much, much greater than L3. And so, we can look at this object and say, yes, this is a three-dimensional object, but we have one dimension here that's much, much less than the other ones. Okay. Similarly, another common example that you'll see is a slender rod. Okay. And so in this situation, we have, one dimension here, L1. Okay. And then I'm going to use two dimensions here. I know it's a cylindrical rod, so technically you only need the diameter. But if we look at the length or the size of the rod in each of those two directions, in L2 and L3, we can use those as comparisons for their lengths. Okay, and so in this situation we have one dimension that's much, much bigger than the other. Right? So we have L1. L1 is much, much bigger than L2, which is about the same as L3. And so technically speaking, you could mesh these objects with a solid element type, right? So you can use a tetrahedron or a hexahedron. Okay. You technically could. ANSYS is not going to stop you. Okay. The issue here is that it's not going to be efficient, okay? Meaning that in order to get a good quality solution, you're going to have to use a lot of solid elements in this kind of small space. Okay? Okay. So you're going to need.
Sorry.
Oh, go ahead, Ivan.
Sorry for interrupting. You mentioned solid elements.
Yeah.
Can you briefly explain what you mean by that?
Yeah. So solid elements are basically the tetrahedrons and the hexahedrons. Yep.
Yeah. I see. Thank you, sir.
All right. And so, we'll dive a bit deeper in terms of, why these elements, why the solid elements are so inefficient. Okay. But, let's take kind of a step back first. Okay. The reason, one reason you can say that the solid elements perform poorly here is that they're kind of ill-suited for these geometries, right? And so if you have a very thin plate, you have one dimension that's much, much, smaller than the other ones. Okay? And same for a slender rod. Okay, you have a one dimension that's much, much bigger than the others. And so you have a mismatch of dimensions. Okay? And so it would be great if you can use elements that kind of capture that kind of behavior. Okay? Or I should say, it would be great if our elements took advantage of these geometrical features. Okay? Okay. And luckily such elements exist, okay? Otherwise I would not bring it up, okay? And so these elements are shell and beam elements. Okay. And so today what we'll talk about is, first of all, we'll kind of, describe why solid elements are poor in these situations. Then we'll talk about what shell and beam elements do differently to make them work a lot more efficiently in these situations, okay? All right, any questions on this so far? Okay, so let's talk about why solid elements perform poorly in these situations, okay? Okay. And so when you have a geometry with a very big disparity in the dimensions, what can happen sometimes is that you can have elements that are just one element through the thickness. Okay, so that's typically how it's described. Okay. And so in other words, if you have your geometry like this, okay. So I'm going to use a thin plate just as an example. And so let's say that you mesh this with hexahedrons. And so let's say that our mesh looks like this. When I say that we have this one element through the thickness problem, what I'm referring to is this, okay? And so if we kind of focus in on this element in particular right here, okay? Okay. Let's look at all the nodes of that element. Okay. All of the nodes on this element are facing the outside, right? So we have all exterior nodes. That means that when you have an exterior node, that means their behavior or their solution values is primarily going to be determined by whichever boundary condition is being applied there. Okay. Okay.
Dr. Chan,
Yes.
what happens if there is no boundary condition applied? Will ANSYS give us an error, or will it assume the value of the nearest node? Or
Yeah. No, we talked about that before when we talked about boundary conditions. So even if you don't explicitly put a boundary condition on a certain face,
yes.
ANSYS does apply a default boundary condition there.
I see.
A lot of times it's called the stress-free boundary condition, which means that there's no load being applied. So mathematically, that may seem kind of obvious, but mathematically that does have a certain form within the code. And so it's kind of important in these situations where that stress-free condition may not be what you want. You don't want it to have undue influence on you.
Yeah, you need to have the right boundary conditions.
Yeah, and not even the right boundary conditions. And so even if you had the perfect boundary conditions in this situation, I would say that if you had just one element through the thickness right here, it would not lead to.
Oh, it'd still be wrong.
Yes.
I see. And that's what you're emphasizing here. The one element in the thickness direction causes errors.
Exactly. Yeah. Because a lot of times, what we're interested in is, especially when you do, structural FEA, although the same thing applies if you're doing thermal FEA or fluids FEA, a lot of things that you're interested in are kind of internal quantities. So for structural FEA, you're interested in the internal stresses. Okay. So for fluids, you might be interested in like flow rate or the pressure. Okay. The thing is, when you're talking about these kind of derived quantities like stress or heat transfer, their value gets a lot less accurate if you don't have interior nodes.
Okay. Sounds good, sir. Thank you.
Yep. And so, a healthy mark of or I'd say a good mark of a healthy mesh is one that has a good amount of interior nodes kind of at all points of the geometry. Okay. So that's one thing that people look for when they're looking at mesh.
Yeah. So I was gonna ask, is there a certain like minimum number of nodes, a general rule of thumb, like make your 3D dimensions a minimum of 5 nodes or something like that? Is there a general rule, or is it just up to the engineer?
There's no magic number. It's generally, the more you have, the better. And so because there can be a lot of derived quantities that you can have computed out there. And so, depending on how derived it is, it's going to require more and more interior nodes. I mean, the bare minimum, I would say, is at least one interior node in there. That's already much better than no interior nodes. But the more that you have, the more reliable your solution is going to be. And then if you later on in the class will learn something called a mesh convergence test, where you basically see how the solution converges with the number of nodes or number of elements that you have in your mesh. And so what you'll see is that kind of the more interior nodes you have, the much easier it is to converge. Yeah.
Sounds good.
Yep. Okay. And so the problem is, one thing that you may say is that, okay, we want interior nodes, so why don't we just, make the elements smaller until we get interior nodes, right? And so one thing that you can do is you can just make these elements just way smaller, right? And so that's one thing you can certainly do. So you can make the elements much, much smaller, and then, you kind of solve your issue by, adding more interior nodes. Okay. The problem is this is not practical in a lot of situations, because in order to get a decent amount of interior nodes in a very, very thin geometry, it's going to require you to have a very, very tiny element size. And that's going to drive up the cost of your simulation significantly. Okay. And so this kind of shows you why that, the solid elements, they may not be suitable for every geometry, especially ones like this. Okay. Okay. And so that kind of brings us to shell and beam elements. So, let's talk about what they do differently. Okay? So shell and beam elements, when you first look at them, they don't look like they're anything special. So a shell element is basically just a two-dimensional element. Okay? So we've gone over 2D elements, and so, we can, those are either your triangles or your quadrilaterals. And beam elements are just 1D elements. So what is a 1D element, you ask? A 1D element is just a line. And so you may be thinking, wait a minute, that doesn't sound special, right? And so, that just sounds like a 2D or 1D simulation, okay? But what makes these special? And the reason why we give them kind of a special name, right? The reason we call them shell and beam elements is that they've been kind of augmented, with additional terms, and they've been designed to work in 3 dimensions. Okay. And so let's go over both of these statements here. Okay, so the first thing, let's talk about the augmentation. Okay. Normally, when you have just a regular solid element type, the finite element solution is going to be solving what I consider going to be the primary solution values. Okay. But when you have a shell and beam element, FEA is actually going to solve for more terms or more solutions at your nodes. Okay. So just to kind of illustrate it to you, for solid elements, what the FEA solves, or I say the first thing that it solves are all 3 dimensions of deformation. Okay. Okay. And so we solve for deformation, and it's an X, Y, and Z. Okay. And then from the deformation, then the FEA will compute things like the stress, which are derived from the deformation. So that's why we call it a derived quantity. Okay. So for shell and beam elements, we compute the deformation as well. But in addition to that, we also compute rotations at the nodes. Rx, Ry, and Rz. Okay. And so what are rotations, you ask? So rotations are basically just they're additional quantities that the FEA solves for that not only show kind of, the linear displacement of the node as a result of the simulation, it also tells you kind of the change in orientation of that element as well. Okay. And that's key because what we can do now, so now that the FEA is directly solving for more quantities, we can use these extra quantities to compute things like stress. Okay? And so even though, visually, what you'll see is that when you use a shell element, it'll look like just a thin sheet, okay? And so basically something with 0 thickness. And so you might be saying, wait a minute, you just told me that, if you have no interior nodes, that's bad, right? And so if you have a 2D shell, then you literally have 0 interior nodes. And so how could that be better? Okay? the reason it's better is because, the shell, we compute these extra things, and those extra things can compute things like stresses a lot more accurately. Okay? And so visually, it looks something like this. And so let's take the same plate, but let's instead mesh it with shell elements. And so a shell representation of that thin sheet from before would look like, this, okay? But at each of the nodes, okay, we're computing dx, dy, dz, okay? So those would be the deformations, and rx, ry, and rc, okay? In other words, we have more degrees of freedom to play with and more degrees of freedom to solve. And that gives us, more accurate results for all the other derived quantities. Okay. We're not going to get into the mathematics behind it. And so, the reason why we have this augmentation is that for the shell elements, we're essentially solving a different equation. Okay. And so because we're solving that different equation, we're able to obtain these extra results. Okay. All right. Any questions on this? Yeah. Wait a second. Rotation? Yeah. What is it? Yeah, so rotation is basically a change in the orientation, or it computes the change, right? And so not only, so let's say that you have kind of a square kind of like this, right? And so at each of these nodes, you can compute its displacement. And so displacement is simply just where the node started and where it's completed. But then the orientation will also tell you, how the geometry actually rotates at that node as well. And so it's not just the displacement, but a change in kind of its shape. You kind of think about that. Yeah. Mm-hmm. Any other questions on this stuff here? Okay. And so the other thing that makes shell and beam elements special is that they're designed to work in 3D. Okay. And so what I mean by that is that normally if you have a 2D simulation, you're only going to compute quantities of interest, or you're only going to have degrees of freedom within that 2D plane. Okay. For shell and beam elements, we actually compute displacements. We call it out of plane, out of plane. Okay. And so, technically, I've already kind of shown it in the red figure above, right? And so normally, if you just have a 2D sheet, right? So if you think back to activity 1, right? So activity 1, that was a pure 2D simulation. So we did not use shell elements for that, even though we did use 2D elements. Okay? The difference there is that in activity 1, when we computed the deformations were only in the X and Y direction because we were constrained within that plane of motion. Okay. But for shell elements, we could actually compute displacements that go out of plane, okay? And that's really key, and that's why we can actually use them together in a 3D situation, because we can actually compute those quantities, okay? And so that's kind of what makes shells and beams different. So it's not just a 2D simulation. It's really kind of these special element types that have their own governing equation that just make them work, a lot more efficiently for some geometries, okay? Okay, any questions on this? Okay. And so you might be asking, when is it appropriate, or when do we actually use shell and beam elements? So there's no hard rule of thumb on this, and so there's no threshold that you have to cross. But there are some I do have my own personal preferences. And so let me preface this by saying that, this is kind of what I feel for this. Okay. But other people have other opinions. So generally what I like to do is I like to look at the dimensions of the geometry in question. Okay. And I like to see how mismatched they are.
When you say mismatch, are you implying the differences in the degrees of freedom?
No, mismatch, what I mean by that is just how different those dimensions are. So you'll see in a second. Yeah.
Sounds good.
Okay. And so let's look at our thin plate, right? And so for thin geometries, we have the distinction where one dimension is much smaller than the others, right? And so, if we use the same convention as before, so call this L1, call this L2, call this L3, okay? And so by mismatch, I basically mean the ratio of the largest dimension compared to the smallest dimension, okay? Or even the second largest to the smallest. And so, you can choose one of those ratios, okay? And so let's say I take the ratio of L1 over L3, okay? Or let's say L1 is the largest dimension and L3 is the smallest one, okay? And so what I like to do for me is that if this is about equal to about 10, okay, so you have a dimension that's about 10 times bigger in one direction than the other one, then that's usually a good sign or a good indication that shell elements would be good, okay? And same thing for slender elements. And so for slender geometries, we have one dimension here that's much bigger than the others. Okay. And so we take the ratio L1 over L2 or L1 over L3. Okay. If this is about 10, then that's when I usually start to consider shells and beams. Okay. So basically an order of magnitude difference in the dimensions. Of course, when you're doing complex geometries, it's not going to work out this nicely. You're not going to have a clean measurement for for the dimension in each direction. It works well for these because it's literally just a square and a cylinder. But it's going to be your judgment call. So I would say the ultimate test that you can use to determine if shell or beams are good is to first just try meshing it with solid elements. Tinker around with the mesh settings. And if you're getting a situation where you have that one element through the thickness, then that's usually kind of the best way to know. Okay. And of course, the caveat here is that at a reasonable cost. And so you don't want to drive up your computational budget, significantly just for one part of the geometry. Okay. And so, just kind of weigh the pros and cons. Okay. Any questions on this? Okay. All right. So now let's start talking about how do we actually create shell and beam elements. So the good thing about ANSYS is that it has quite a few robust tools for producing shell and beam elements. And so we're going to be covering a lot of that on Wednesday, or we're going to be demonstrating it. But let's talk about actually what's kind of happening underneath the hood. Okay. So let's start with shells. Right. And so just like we've been talking about, a shell is basically a 2D element. Okay. And so it's basically an element with infinitesimally small thickness or almost negligible thickness. Okay. And their main purpose or their main use case is to represent geometries that are very thin. Okay. All right. So visually, when you look at a shell element, it's going to look like a thin piece of paper, like it has no thickness at all. Okay. It does have a thickness, so the thickness is there. It's just represented in a different way. Okay. And so, the thickness, when you have a shell element, the thickness is stored more as a material property rather than a geometric property. And so very similar to things like the Young's modulus or the density, right? So those are properties of the material. And so every element knows what its Young's modulus is. Okay? And when you have a shell element, there's just an additional property that gets added to it, which is the thickness. Okay. And so it looks kind of like this. And so, let me go back to our thin plate example. Okay. And so the thickness of this plate, just to be consistent with it for, is L3. Okay. And so what we'll see is that, to create a shell element, most of the times you're going to be basically modifying a three-dimensional CAD, okay, and then transforming parts of that three-dimensional CAD geometry into a shell, okay. And so when you turn this to a shell, it's going to look something like this. And so visually, it's going to look like a piece of paper, okay? But in reality, all the elements on the shell, they have an additional property called thickness, okay? And it's going to be equal to L3, okay? So the thickness information is not lost, okay? So I want to make that clear. So even though visually you don't really see the thickness, it still is there. It's just represented as a material property, okay? And like I mentioned before, when you have shell elements, you're essentially solving a different governing equation, okay? The governing equation is modified so that, you can incorporate the thickness as, as a variable like this, not something that's represented geometrically. Okay. All right. And so in general, there are 4 different ways to create shells for FEA. Okay. Some are more common used than others. But then, we'll talk about that. Okay, and so the first way is to create just a 2D sketch and assign it to be a shell. And so number 2 is to create an open sketch. And so an open sketch is one that does not close on itself. And then we can use some additional CAD tools like extrusion or revolve or sweep to generate, planar surfaces. So method 1 and method 2 here, I would say those are less common because in order to use method 1 or method 2, you kind of have to design your part, or you have to kind of CAD up your part from the very beginning with the intention of making certain parts, shells, right? And honestly, if you can do that, that would be kind of the cleanest way to do it. But it's just not that common. Because a lot of times when you are running FEA, someone else is creating the CAD model for you, and so they're not really going to make your life convenient because that's just not how life works in general, right? And so a lot of times you're going to be receiving a CAD model that's fully designed in 3D, and you're going to be modifying it to be to have shells or beams as you see fit. Okay. So method 3 is the one that we'll use most often. And it's the one we'll make use of a lot of in the activity on Wednesday. Okay. And so method 3 is to use something called a mid-surface tool. And so the way the mid-surface tool is that the way it works is that you select 2 surfaces or 2 faces that are parallel to each other and very close to each other. And then what it does is that it creates a shell kind of in between. Okay.
Professor,
Yep.
will you be showing us how to do this in the actual simulation?
Oh, of course. Yeah, we're gonna walk through it together on Wednesday. Yeah. But there's gonna be a lot going on Wednesday, and so I want to kind of prep you just to kind of show you what we're going to be doing. But yeah, I'm going to be walking you through it every step of the way. Yeah.
Thank you.
Yep. All right. So method 3 is the one that's most common. That's the one we'll be using kind of exclusively on Wednesday. Okay. But there is a fourth tool within ANSYS itself, and so use it's called the thin surface tool. Okay. And the way this works is that you basically select a solid object, and then the thin surface tool will create a shell from that, and so it'll basically hollow it out. And so just in the interest of time, I want to make sure I kind of get to the end of the lecture notes today. I'm just going to talk about mid-surfacing because that's the main one that we are going to use on Wednesday. Okay. So I want to show you how it works visually. And then the other 3 methods, you can look, we can just kind of discuss those more kind of, if we have time at the end. Okay. Okay. So let's talk about mid-surfacing. Now, so the idea behind mid-surfacing is that if you have two surfaces that are parallel and very close to each other, then that means that that's probably a thin part of your geometry. And so what the mid surface essentially does is that it takes those two thin parallel surfaces, or it takes those two parallel surfaces and then just kind of eliminates the thickness between them. Okay. All right. And so just as an example, let's see. Okay. And so the way it works is that if you have a situation, and so let's say that you have a geometry that looks like this, okay? And so on the one hand, you have this surface on this side. Okay. So we'll call this surface 1. Okay. And then behind the surface, we have another one that's exactly parallel to it. And so it's a little bit hard to draw, but it's basically the surface that's kind of outlined here. Okay. So we'll call this surface 2. Okay. Right. And so the way this tool works is that, in ANSYS, what you're going to do is you're going to click both surfaces. Okay. And once those two surfaces are selected, then you tell ANSYS that I want to do a mid surface here. Okay. And then what's going to happen is that one shell is going to be placed right in the middle of these two parallel surfaces. Okay. And so the result of this is, use pink. And so this pink shell, okay, this is now a shell, and so that thickness is eliminated. Okay. Okay. So now this shell here kind of represents that geometry, where previously, you actually had something with thickness. Okay. So previously you had something like this. So let me go ahead and draw it in dotted lines. For some reason, this was very difficult to draw. Okay. Right, so when the dotted lines represents what the geometry was before the mid surface, okay, and the mid surface basically eliminated that thickness and then replaced it with a shell. Okay, so this works really great, and a lot of geometries kind of follow this pattern. Okay, and so you can use this, for all those cases. Okay, and so once again, I'll walk you through this on Wednesday. So I'm not just going to throw you to the wolf, but I just want to show you kind of what's going on there. All right. Any questions on this?
Is the shell exactly in the middle of both the surfaces?
Yes, it's exactly in the middle. Mm-hmm. So that's actually going to create some issues too, because what you'll see on Wednesday is that when you can't just eliminate thicknesses willy-nilly, because you may have something like you may have another geometry here that's connected to this one here. Okay. And so in the original geometry, it's fine because you have the thickness and it's connected there. What we'll see on Wednesday is that by eliminating that thickness, then those parts are no longer connecting. And so you actually need to modify the geometry further to make sure that the different parts actually connect. So even though it's put right in the middle, it's still not perfect.
And what's the minimum thickness for it to be worked? What's the minimum thickness that needs to be worked?
It should work with almost anything as long as it's thick enough that it has significant figures. As long as the program can recognize that there's actually some thickness there, and so you can use that for almost anything. There's no maximum, I believe, either, but of course, the farther they are apart, the more inaccurate it's going to be. If you have a fairly thick part, it's better to use solid elements for that, because the shell is not going to capture that as well. Any other questions on this? Okay. All right. So let's go ahead and move on to beam elements. Okay. And so a beam element is a 1D element that's meant to represent a slender geometry. And so remember, we defined a slender geometry to be something where one dimension is significantly bigger than the other one. Okay. And so when you have one dimension that's significantly bigger, then the other two are considered insignificant. So that's why we represent that with the 1D element. Okay. And so very similar to the shell element, it stores some additional properties, right? And so if you think of the shell element, the thickness is something that's stored as a material property. Okay? For beams, it's actually a little bit more unique. And so for beams, they actually have to store more complex information than just the thickness. Okay? Beam elements have to remember what its cross-sectional area was and what its cross-sectional shape was before turning into a beam. Okay? So for example, if we go to our kind of our quintessential example of a beam element, okay? And so let's say we have a cylindrical rod. And so when we turn this into a beam, it literally just becomes a line. Okay? So you may think, that's pretty straightforward, right? So we have a cylinder that turns into a line. Okay? Let me give you another example. And so instead of a cylindrical beam, let me draw an I-beam. Okay? Why did I draw an I-beam? God. Had too many near-death experiences this weekend to draw that accurate, but you get it. It's an I-beam, all right? So it has an eye cross-section. Right? Okay. And so when you turn this into a beam, it's going to look exactly the same as above. So it's going to look like a line. Okay? Should have done a square. Why didn't I do a square? That's way easier to draw. Anyway, okay. So visually, these two, the top and bottom, when you turn them into beams, look the same. But obviously, these two beams are different, right? The top beam has a circular cross-section. The bottom beam has an eye cross-section, right? And so in order to differentiate this, what the beam has to store, okay, beam must store its cross-sectional information. And that includes its shape, but also its dimensions as well. Okay. And the way it does this is that it basically stores it as a sketch. So inside each beam is basically a sketch of what its cross-section looks like with its dimension. So normally this is not something that the cross-section information actually is quite a bit more complicated than the thickness. So normally it's not something that you have to really think about unless you're making a beam from scratch. But I do want to let you know that that information is not lost. It's still there, and it still does make an impact based on the equations. Okay. All right, so there are two ways to make a beam. And these two methods kind of follow the same, kind of in the same spirit as the shell. Okay? And so there's method one, where if you're, if you're creating the CAD model from scratch for the explicit purpose of FEA, this would be the better method. Okay? So method one would be to create a 1D line sketch. And then assign that to be a beam. And so that's the cleaner way to do it. You're going to end up with a much cleaner geometry as a result. Okay? But in reality, that doesn't happen all that often because you're usually not the one creating the CAD. Okay? And so the second way is to use a tool called extraction. And so by extraction, all you have to do is click a you click a slender part of your geometry, and then ANSYS immediately turns that into a beam. And the nice thing about method two is that it preserves the cross-section information. So it kind of stores that automatically for you. Okay? And method two is what we're going to be using in the activity. It's actually quite nice. And so it's actually very convenient to use the extraction. So it's really just, you turn the tool on and you just point and click at the different places. Okay. Okay. Any questions on this? Okay, all right. And so that's kind of all that I wanted to talk about with regards to kind of the properties of shells and beams. The last thing I want to get to today is to talk about accuracy and convergence of shell and beam elements. Okay. So when we talk about accuracy in an FEA simulation, accuracy refers to how how realistic or how accurate or how well your simulation predicts reality. Okay, so the more accurate your simulation is, the better representation of reality it is. Okay, and we've already kind of discussed the fact that generally the smaller your element size, the more accurate your simulation is going to be. Okay. Right, so that's undeniable, and so that's kind of one of the universal truths of FEA. Okay, and so in a perfect world where we have kind of limitless resources, right? Shells and beams would be a non-issue because all you would do is you would just create your geometry and you just mesh the hell out of it. And so you create meshes with millions, billions of elements. You get the most accurate thing in the world, and it'll be beautiful, right? In reality, we don't have that kind of luxury, right? So we're limited to resources, and so. Not only is it important to know that, more elements give you an accurate result, what's kind of more important is how efficiently can you get to that accurate results in the least amount of elements. Okay? right? So it's like shopping for groceries, right? So you want to get the most amount of food for the least amount of money, right? And so, when you talk about accuracy, it's not just a matter of getting an accurate result. It's, how efficiently can you get there, okay? And so, I've brought this up several times, but I guess now is kind of a good time to talk about it more specifically. So the way that we kind of measure this is through a test called convergence, okay? And so convergence basically is a test of, exactly what this is, of, how quickly can you get to an accurate result, in terms of the number of elements, okay? Okay. And the reason we call it convergence is that, once you kind of reach a certain point, right? So there's no, accuracy is not something that you can keep getting infinitely better at, right? After a certain point, you kind of reach a point where like your simulation is accurate enough, okay? And so, when you say that your mesh is converged, you've basically reached a point where if you refine the mesh any further, you actually don't get any improvement in your solution, okay? So every simulation is a point So every simulation has that point. So there comes a point where, if you keep refining the element, you're not really going to be getting it. You might get like very minuscule changes, like, you might get changes in like 0.001 deformation of the result. That's always going to be there. That's numerical kind of precision error. But, for realistically speaking, there's a point where it doesn't change. Okay. And so to measure this, we can create something called a mesh convergence plot. Okay. So this is a mesh convergence plot. And so on the x-axis, or I should say the horizontal axis, we have the number of elements. Okay. There's some variations on convergence plots. Some people like to put element size on the horizontal axis, but personally, this is my own opinion, and so other people feel differently. Personally, I like to have the number of elements on the x-axis, on the horizontal axis. That way you're converging to the right versus converging to the left, just because that's just how I like to see things. Okay. And on the vertical axis, we have the solution value. And so that could be something like a stress value, it could be something like a deformation value, something that you're interested. Ideally, it should be, the thing that's hardest to converge. So these are usually things like stress, which are derived quantities, but sometimes you're just interested in the deformation, and that's okay. Okay. Right. And so when a mesh is converged, your convergence plot would look like this. And so usually, you'll start at a point. Okay. So let's say for a very coarse mesh, you start with a certain number of elements, and then as you increase the number of elements, your solution value is going to change. It's going to, and so in this case, it's steadily increasing, but it could also decrease. And then eventually you'll reach a point where the plot will start to plateau. Okay. And so in this region right here, this region is what I would consider to be mesh converged. Okay. And so at this point, within that plateau region, you can keep increasing the number of elements. So you can keep refining the mesh. You're just not going to get any benefit from it. Okay. And so you're basically doing extra work for no benefit at all. Okay. And so the ideal mesh would be probably somewhere around, here probably, right? So right at the beginning of the mesh convergence region. Because from there, you get, as accurate of a result as you can, for the least amount of work, for the least amount of elements, okay? Right. So why am I bringing this up, right? And so this may not have much, this seems like it doesn't have much to do with shells and beams. So the reason I'm bringing this up is that shells and beams, for the situations where they're appropriate, so when you have thin and slender geometries, they reach convergence a lot faster than the solid elements.
Is that also to say that shell and beams help make the competition more affordable?
Absolutely, yeah. Because when you use shell and beam elements, it's going to reduce your element count by a significant amount. It's going to reduce your element count by a significant amount, and it's going to increase the accuracy of your simulation. So it's like a double punch of awesome.
That sounds good.
And so if you look at the convergence plot, okay, and so let's say that we're running the exact same simulation, so the exact same CAD geometry, the exact same boundary conditions. In one situation, we're going to use, just the solid elements, so maybe just tetrahedrons or hexahedrons. And then in the other situation, we're going to use shells and beams for all the thin and slender geometries, okay? And so it would look something like this. And so just like above, we have number of elements. And on the vertical axis, we have the solution value. So for the solid elements, the solid elements might look something like this. Let's say this is solid elements. Of course, these are all approximate. I'm not drawing any numbers on these axes, and so there's no magic number between these. Okay, but I drew kind of an extended kind of slope period to show that it takes a long time for solid elements to converge. Okay, if you compare that to shells and beams on the exact same geometry, it's probably going to look something like this. I should connect. So this is shell and beams. And so your ideal mesh for the shells and beams is down here, whereas your ideal mesh for the solid elements is probably somewhere like out here. Okay. And so for shells and beams, you reach convergence a lot faster. That means your simulation is going to be a lot cheaper. It's going to finish a lot faster. And, in general, it's going to look, a lot better. Okay. So this is kind of important. So this is kind of the main reason why you use shells and beams. It's so that you can get an accurate result for a lot less computation work. Okay? It's going to be a lot more manual work. And you'll, this week is probably the biggest swing. So, I've kind of been tracking the feelings of my finite element classes for the last few years. This week is probably the biggest swing in the feelings of the entire week, of the entire semester. Because, usually, we start the week off with this lecture and everyone thinks like, wow, shell and beam elements, those are awesome. Like I'm going to use them for everything. And you actually go and try to use them in practice and you're like, shells and beams suck. I'm never going to use them again. So it's a lot of manual work. But sometimes it can be, for the cases where it works really well, it works really well. So it's worth the effort. But, I expect a lot of people to be cursing my name on Wednesday when we're doing this activity because it's, honestly, this is probably my least favorite activity, just because there's a lot of places where things can go wrong. But it's important. We have to cover it because it's an important part of FEA. Okay. All right. Any final questions on this before we wrap it up for today? Okay, all right, so that's all we got time for today, and so I will see everyone back here on Wednesday for the activity. So hope you guys have a good night. Thank you guys for coming out, and yeah, see you on Wednesday.
Thank you, Dr. Tron.
Thanks, Ivan.
Professor,
Yep.
I have a question. If we can't make it to the office hours you have set, would it be possible to like schedule like a 30-minute Zoom call on like Thursday or Friday?
Yeah, absolutely. Yeah, just email me. I know those office hours aren't going to work for everyone, especially you guys are grad students, so you guys are really busy. So just send me an email, and then we can try to find a time that works for a Zoom call. Yeah.
Thank you. Yeah, I started a new job and it's all the way in Palmdale. So
Oh, dang.
yeah, so and I get off like at 4:30 and driving home, I don't get home till like 6. So yeah, I've been really trying to, thank you. I appreciate it.
Yeah. Just email me. We can set up a time.
Thank you.
Professor,
Yep. What's up?
I wanted to pick your brain over the midterm because
Okay,
you
sure.
said we could do that.
Sure. Of course.
So I've got some ideas for the globe